Hello, my name is Naomi Hagan, and I'm a physics major here at Drexel University, and I'm part of the STAR Scholars program. My research is on creating machine learning training datasets to observe kilonovae with the Hubble Space Telescope and the James Webb Space Telescope. So, a little bit of background on what a kilonova is. When we have two incredibly dense celestial objects colliding in space, we get what's called a kilonova. They're incredibly short-lived and very difficult to detect. We've only had one successful detection to date, so what our research aims to do is change that. So we're employing machine learning. This is the second part of the background is on machine learning. So what is machine learning? This is when we feed in a huge data set to a computer. We give it a multitude of different independent variables, as we call them parameters, and it learns to predict a certain dependent variable based on what we've given it. So the dependent variable that we're looking for here is what we call signal to noise ratio. In general, the higher signal to noise ratio, the better the picture is that we're getting back. So the signal here being kilonova and the noise being the background radiation of space. So some of the parameters that we're putting in look like the observation angle, observation time, observation distance, the exposure time of this, which is just the time that our picture is actually accumulating data from our source, and different filters. These are all what we call parameters. And we take different combinations of these parameters to get a certain signal to noise ratio, which we know to be true. We feed it into the computer, and the computer will learn to predict based on what effect each parameter has on the dependent variable or signal to noise ratio. So for a quick example, let's talk about observation distance. So as we increase distance, generally we're going to expect the signal to noise ratio to decrease. As distance is increased, I mean, we're farther away, we're getting less signal, there's more interference, all sorts of things like that. So our trend is that as distance increases, we get the lower signal to noise ratio, and the computer will learn this, and it'll take, okay, so we have this model at a certain distance and this model at a further distance. Well, the signal to noise ratio for the further distance is going to be less. So that's what my research has mainly focused on. And what I've been doing is creating codes to create these training data sets. Our final concrete product is a set of it's thousands of different combinations of parameters. The standard size is 10,000 plus entries into our data set. And it's just all different combinations of different parameters and the signal to noise ratio that it gives that we know to be true. So the further research that can be employed by this is, one, actually being able to observe these events by having the proper means of observing them through these telescopes. And also, we can create more comprehensive training data sets in the future based on even more parameters. So that's the scope of the data here that we have. And just a quick preface, the research is mostly focused on the Hubble Space Telescope, although it does pave the way to work on the James Webb Space Telescope, although we only had 10 weeks to do the research. So that's the biggest drawback to the research for now, but that's what we've done. So yeah, thank you for your time.